here. All right. So, as everybody is logging into the Zoom, thank you all for being here tonight. We have our presentation, Understanding Geothermal Energy. My name is Kian, and I am an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement. Before I introduce our speakers tonight, there's a couple of rules that I want to go over for everyone joining us online. So your cameras will remain off and you will be muted throughout the presentation. So if you have any questions, please type those into the chat or the Q&A, and our presenters will answer those throughout the presentation as they come in, or at some point after the presentation. Following the presentation, we have a very brief survey that only takes about a minute to complete. This survey helps support programming like this one, so we appreciate everybody taking the time to fill those out. Tonight, we welcome Vishal Khanna and Kyle Wilkinson of Advanced Engineering Systems Incorporated. Vishal Khanna has over 40 years of experience in designing and commissioning of mechanical systems and has served as principal in charge for significant higher educational clients. His expertise is in HVAC, plumbing, and life safety fire protection design for educational, government, healthcare, military, industrial, residential, and commercial facilities. He has a Master of Science degree from Syracuse University, New York, and is registered to practice engineering in 35 states. He is passionate about sustainable and environmentally friendly projects, and his vast experience includes around 30 geothermal systems in many states from Wisconsin to Texas. Kyle Wilkinson has over 22 years of experience in designing and commissioning of life safety and mechanical systems. Kyle has worked with clients on projects ranging from energy analysis and life cycle cost analysis to developing full contract documents, as well as services during construction. Kyle's expertise is in HVAC, plumbing, and fire protection design for research facilities, as well as educational, governmental, commercial, residential, recreational, and industrial facilities. Kyle places much emphasis on sustainable and environmentally friendly systems. His past experience in construction, as well as his academic background, provides practical experience in designing, testing, and analyzing mechanical systems. So thank you both for being here tonight. I'm excited to hear what you have to say, and I will turn it over to you two.
Well, thank you.
Great. Thank you for that introduction. That was very kind. And thanks to the Conservation Nebraska group as well. Thank you for all the attendees to spend your evening or late afternoon, early evening with us. Just wanted to talk a little bit about the geothermal systems, geothermal energy, how it affects the environment, and how Peru State College got involved in this geothermal system, which is kind of a first of a kind, not just in Nebraska, certainly in the Midwest, but probably around the country as well, where campus-wide, they're looking at going and putting in a centralized geothermal system. So Kyle, if you want to get to the next slide.
Not clicking here.
Uh-oh.
There we go.
Yep. So some of the topics we'll go through today very quickly. How does the geothermal system work? We'll talk a little bit about the many different types of geothermal. People have some connotations on what is geothermal. So there really is a lot of different types. It could be open loop. It could be using pond systems, water bodies. It could be vertical boreholes that you dig down into the earth. It could be horizontal systems. We'll talk about that. Then some of the design considerations, what really goes into this. It's a lot of science, but a lot of art as well, just past experience, but a lot of actual calculations that go into it. We'll talk about some example projects, and a lot of them will be what we have done for Peru State College because this client has really committed a lot towards that. We'll talk a little bit about economics as far as the paybacks of a geothermal system, what a system like this may cost. And then finally, we'll just get to some questions. If you have any, we'd be glad to answer those for you. Next slide, Kyle. I'd like to start by saying kudos to Peru State College. They have done a lot towards energy efficient systems, low maintenance systems, and sustainable HVAC systems. The college has standardized around these geothermal systems. Basically, if they can afford it, if any new project comes up and they can afford it, they want to use this sort of system. We started with Nebraska State College system back in 2011 when we did the first project for Wayne State College. And you see the three campuses that they have. They have a campus in Chadron at the northwest corner of Nebraska. They have Peru State College at the southeast corner of Nebraska, diagonally opposite, Wayne State College up northeast. And then the headquarters for the system office is in Lincoln. So in 2011, we did our first project for Wayne State. We went up there. They had a central plant that has chilled water systems and hot water systems to condition the entire campus. We went in there and we gave them this option of going geothermal, and they said, "Wow, we haven't done that. Is that really going to be good for us?" And we proved to them that it's a great system, low maintenance, and so they proceeded with that. And since then, we've done 3 or 4 different projects for Wayne State College. In 2014, they recommended Peru State College talk to us. We started with our first project out there. And since then, we've done more than a handful of buildings that we'll talk about just shortly. The next slide, Kyle. So how does a geothermal system work? It basically uses the ground as a solar battery. It takes the energy from the sun, and believe it or not, a lot of it, almost 50% of that energy is actually absorbed by the ground. It takes that, and the ground can then be used as a heating source in winter and as a cooling source in summer. So it's almost like getting not quite free, but almost free energy. So very, very cost effective as far as that goes. Next slide, Kyle. The chart you see here is throughout the United States, the temperatures that are average across the regions. For example, Nebraska in the middle of the state, you see we range from anywhere from about 50 degrees to about 54, 55 degrees, depending on which part of the state you are in. Peru State College is right around the 53, 54 degree mark. When we design systems, we have to do tests to actually find that out. As you go deeper into the earth, it obviously the temperature stabilizes right at the surface of the earth. It's whatever temperature you see. It could be minus 10 degrees in winter and probably over 100 degrees sometimes in summer. But if you start going down below, and this is just a schematic of an elevation, if you went about 20, 25 feet down, that temperature just seems to stabilize and stay at those temperatures I just mentioned to you, the 52, 53, 54 degrees or so. Even about 8, 10 feet down below, it seems to be very close to the 53, 54 degrees. It could be off by 5 degrees here or there. The boreholes that we go in and dig, they actually go anywhere from 200 feet to maybe, there's a project that we'll talk about that went about maybe 630 feet deep. And so the temperatures you get out from the earth are very stable and very consistent. And they're used for, like I said, heating in winter and cooling in summer. Next slide, Kyle. So in very simplistic terms, if you were talking of a facility or your house, the left side of this schematic that you see over here is the winter months, where you're trying to heat your house. So the red, the number 2 is where the water is coming up from the ground at about 52, 53 degrees. It goes into your heat pump that heats the air inside that heat pump. And with the result that that water becomes quite cold, maybe 10, 15 degrees colder, 10 degrees colder, and it goes back into the earth through the heat exchanger. It heats, comes back up. And so that's how you're almost getting some free heat from the ground in winter. Conversely, in summer, the other extreme, you're trying to cool your house so that 53, 54 water is actually cold water because the temperatures outside are approaching 80, 90, 100 degrees. So you take that cold water, it comes into the heat pump, it cools the air down that you distribute through your house, with the result that it actually warms the water, which is the red that Kyle is putting his cursor, and it goes back into the earth, and the cycle continues. So you almost get kind of free cooling in summer. And during times of mild weather, it could go either way. Very, very simplistic approach, but that's essentially what the geothermal system does. Next slide, Kyle, and I think you might want to talk about this.
Yeah, so as Vishal mentioned, there is lots of different types of geothermal systems. The most common one are closed loop systems, and that's the ones we were just showing where the water in the pipes stays in the pipes. It's not mixing with any groundwater. The vertical boreholes are the most common installation that you'll see around. This is a picture of horizontal bores. This is a machine that installs the vertical bores. So the vertical bores could be anywhere from some are as shallow as 150 feet, but they could be 600 feet, 650, or even more. And they're all around Nebraska. They're about 6 inches in diameter, the size of the hole that goes all the way down. Um,
The
so then
size of
you
the
can,
pipe itself is more like 3/4 inch or 1 inch tops, but the
yeah.
hole itself is, yeah.
So, and this actually is vertical bores. I'm sorry here. These are vertical bores here, and then they're connected with lateral piping. Horizontal bores are similar. They just drill the pipe across through the ground horizontally as opposed to vertically. The well fields can be configured in different ways. You can have one well field per building. You can have several smaller ones per building. You can have a few holes per heat pump. There's different ways to do it based on the ground available and where the equipment is sitting. But again, this is the most common type that we tend to see. So the horizontal loops, here is if you come and you dig out all the ground and you lay the piping out and then you bury it. Like I said, they can also come in and bore horizontally like they would any other utility pipe. These things, they call them slinkies because they look like a slinky. Uh, the the deeper that you can bury them, the better, because like Vishal said, the ground temperature is more stable. You would need more pipe the shallower you get.
And that
You can,
system is a little less efficient than the vertical one that Kyle had mentioned.
yeah, you can also put them. So we've also used the term heat exchanger a few times here. So the heat exchanger is the pipe. The pipe in the ground is the heat exchanger. And here is an example of a pond loop. So you can install that horizontal heat exchanger in the ground, uh, but then you fill it up with water, and water moves the energy much better than the dirt. One thing also to mention, I'll go back a slide here. You can kind of see it right here. So they drill the 6-inch hole, and then they put the pipe is in the shape of a big U, and they put a weight on it and a rod, and they force it all the way down, and then they fill the hole with a thermal grout, and that helps the energy go from the dirt into the pipe because air is more of an insulator. So if you have a hole with a couple pipes in there, it's the energy is not going to get from the dirt to the pipe. So they fill it with grout, and that helps form that bridge so the energy can get to the pipe and out of the pipe into the ground. So another type, so those were all closed loop because the water just stayed in a circle essentially. And then there's other kinds, an open loop, where you're pulling water out of the aquifer, you're heating or cooling it, and then you're putting it back down into the aquifer as well. Uh, these are not quite as common that we see, and there is different types. So you can pull out from a couple wells called like supply wells, and then you can have rejection wells as well. The one over here, we've done a project out in Hershey. It was a single well pump and dump, so it was a little unique that it was pulling and pushing back into the same well. So this was one big hole that they would put in. There was a plate here that would stop the flow to keep the flows separated, the ins from the bottom and the outs on the top. But this is a little more. It's harder to do these types of systems because you got to have the right amount of aquifer spacing and water depth and all that. You have to work with the state as well. So here's another example. So what is a system going to serve for design considerations? You can use the water for lots of things. Most commonly, they're used for heat pumps. The heat pumps are able to use that cooler water for heating and then warmer water for cooling. Typical temperatures in the heating, like Vishal said, could be around that 50 degrees or so mark. And then in the summer, they could be designed anywhere from 70 to about 85 degree entering water temperature. The ground generally will do about a 10 degrees difference between the supply and return. So we have to design it for that. Um, So so all the different design configurations. So it's not just like a rule of thumb thing. So we have to go through different calculations. We look at the load. What's the heating load? What's the cooling load? Is it heating dominated? Is it cooling dominated? What's the load profile? Does it spike really high and go down, or is it more constant? All these affect how you're trying to use that energy from the ground. If you don't have enough wells and it's not designed right, you can over time start to either pull too much heat out of the ground and it cools down, or it can do the opposite and it can start to heat up. Uh, you can see some well fields that are undersized, that are heating up too much. They may have snow melting off of them because they've stayed too warm. Um, but in general, it can be a pretty flexible system, but you do have to design it right. Um, So the annual equivalent full load hours, so that's also a measure of how often is it running. If you have a building like a church and it's occupied a couple times a week for minimal hours, it would have low usage. If you have a hospital or medical office building, it might be operated a lot more. So your annual equivalent full load hours is much higher, and that all plays into it. You can also use the heat pump systems for other stuff. You can use it to make hot water for snow melt, process cooling. You can use it to make domestic hot water as well. Other things, like I said, there's a lot that goes into it. It's more of a science than an art. Did my screen just go away?
Yes.
Oh man, what happened? I apologize about that.
Looks like it's coming back.
Okay. I don't know what I clicked. I apologize.
That happens.
Okay, here we were. More design considerations. So the ground temperature, which Vishal talked about earlier, is fairly constant around here, but we do have to measure it and see what it is so we can put that into the calculation program. Thermal conductivity is a measure of how well the ground, I guess, essentially moves the energy, and thermal diffusivity is kind of the same type of thing. So we use those two values and the deep earth temp to help in the design help in the design calculations. Uh, Other things to consider is the depth of your wells. Sometimes it's better because you don't have much space, so it's better to go deeper. Other times you want to keep it more spread out. If you have more of a heating dominated design, you might want to keep everything more tight together. If you have more of a cooling dominator, might want to spread it out more. So whether it's square, rectangular, and the spacing between the wells all plays into how well the energy is transferred. Typically, 20 feet is a common distance between the wells. And we said before, 6 inches is the well, and then you have your grout, and you have your roughly 3/4 to 1 1/4 inch pipe, depending on how much flow you're trying to move through it. This is an example of a test machine here. So a well driller could be hired to come drill a test well. They'll have the pipes come up and hook up to this, and then this will heat the water, and they will measure. They know how much energy they're putting into the water, and then they measure the flow rate and the temperature in and out, and then they're able to calculate these based on that.
And Kyle mentioned the 20-foot typical spacing. So if it was heating dominated and you're in Wisconsin, we did a project out there, the wells get closer apart, together. They're
Yeah.
like 15 feet apart. You go down to Texas and it's the other way around. You may be 30 feet apart.
Mm-hmm.
So it just makes a difference in whether it's cooling dominated or heating dominated climate.
Yep. And we do take more of a, like I said, more of a science approach than an art. So
Yeah.
instead of just saying rules of
Hmm.
thumb, it's going to be
Yeah.
this, let's hope it works. We go through, you can kind of see, here's an example of a spreadsheet that we have, and we do use this program from Dr. Kavanaugh, who helped write the book on the ASHRAE for it.
The
And
design manual by for the American Society of Heating, Refrigeration, and Air Conditioning Engineers. It's kind of a design guideline. It's probably the Bible for geothermal systems.
yes, yeah, I should have said that. Yes, thank you.
Yep.
Uh,
Mhm.
and so these are all the factors that we put in, and then it spits out different results, and then we can go, it's a little bit iterative. And then based on what it's telling us, we can go back and tweak it. Hey, we want to add a little bit here. We want to change the shape or whatever. And then we can get something that works per project and make sure we believe it will work and has a little bit of safety to it. So this is an example of the output. And so you could look, like I said, if the well field is undersized, you can run into long-term ground changes in temperature, and it'll happen over a while. And so this would be an example here. So with minimal groundwater movement, it's saying, I don't remember how many it was in here. This probably says down here. So this was a 5 by 20 grid. And so it was telling us we would need 314 feet per bore. And that starts 5 feet down because your wells all start about 5 feet down because that top 5 feet is not used. That your piping is going horizontally back into the building, roughly 5 to 4 feet underground. And so you can see all the parameters here.
And then the bottom arrow, Kyle, it does, just tells you that our design for this case raises the Earth temperature 7/10 of a degree over a 10-year period. So you really want to minimize that impact. And after that 10-year period, it really does not tend to heat much more than that. So it's kind of 7/10 of a degree is what we're heating the Earth in this cooling dominated climate.
Mm-hmm. And then here's a couple details that we'll use on our drawings. And so say we have, 10 GPM here, and then we were going to distribute that 10 GPM into these 4 holes. So that's how it would distribute. So the water would come, it would go through. This is called a reverse return fashion. So it's first supply, last return, and that kind of inherently equalizes the flow. So you don't get too much flow through one well. This might be a little bit in the weeds, but just so you know. So they all pipe together. And here's kind of a side view of what we were talking about. So you go down about 4 to 5 feet, and that's where your laterals would run that we saw in that picture. And then it runs over, and here's where your well is started, and it will go down. 300 is a somewhat typical value around here to start from, and then you might go deeper if you need to. So the next
And
one, we'll talk about Peru State College and some of the specific examples there.
yeah, that slide, I just want to point out that Kian did put in the chat saying if you have any questions, please do feel free to type them in the Q&A and we may get to them now or towards the end. This is kind of a bird's eye view of Peru State College, their campus. You will see those circles, 1, 2, 3, 4, 5, 6, 7, almost 8 buildings that are now on the system, on the geothermal system. There's 3 or 4 that tie into the quad buildings. In the quad, we'll talk about that in just a bit. But we had first started off, Kyle, if you want to go to the next slide, I think that we'll talk about the TJ Majors well field. This was the classroom building that was the first building we did for them. You see the top bird's eye view on the top right corner.
This
Back
was
in
right. This was this one over here.
right here, yes, yeah. So that was back in 2014 when we did their first building, and it was a huge success. It changed. We did some remodel. There was an attic space that was actually inhabited by birds, and it was just a horrible mess. We actually opened it up completely and made a mechanical room out there. It became you could just walk up the stairs to that mechanical room, put all the heat pumps out there. The heat pump piping, you'll see this, the on the bottom left is the picture where we actually went and used that ground to put in our boreholes, where we put in 70 boreholes. And in this case, because of the size, they were 450 feet deep. Now, the ones you see on the right, the red were not possible because there was lots of trees and grade issues.
And
But
sloped.
yeah, it was sloped quite a bit. And yellow are the ones that we actually used to put the vertical bores going down. Then we connected all that with the horizontal laterals and brought it into the building from across the street. Yep, right there across the street. And so that was the first project we did. Like I said, it was a big success. They were happy with it. The other advantage of this is it's a closed loop system. So the water quality does not matter. Out here in Peru, Nebraska, it is extremely hard water. In fact, one of the first things we heard when we went out there, they said, don't wear white clothes. You can't keep them clean. The water is so hard, you can't keep them clean. So the water quality is a big deal. These are closed loops. So once you fill it with good conditioned water, you really don't need to take care of that. There's not much maintenance to that closed loop system. And so it really helps as far as maintenance goes. It also reduces maintenance dollars. Next one, Kyle. The theater at the east end of campus, kind of east of the quad, was a building that we redid. It was there was an addition that was put on, and the entire facility was remodeled. As part of that, on again the east side of that, you see these green dots. Those were the vertical boreholes that you get the free heating and free cooling from. We put in 60 boreholes and they were 300 feet deep, as opposed to TJ Majors were 450 feet deep. So depending on the tests and depending on the site available, you come up to see how far apart they are, how deep they are, and how many you need.
300 to 350 is kind of your best bang for your buck.
Right. Yeah.
If you have the ground.
The administration building was kind of a different beast when we started off with it. They had a cooling tower that was serving a cooling tower and a boiler, heating and cooling, that was serving this building. And the cooling tower was failing for the same reason I just mentioned to you. The hard water was really messing up that cooling tower. They could not keep it clean. It came a time when they had to replace the cooling tower to cool this building down. And so rather than spend money in doing the cooling tower, we used their existing heat pumps that were inside the building, but instead of using a cooling tower and a boiler on the outside, we went and put these boreholes. There was 35. We put them in a parking lot to the south of this building. You see the building in the red towards the top left of your photograph. Yes. And then to the right side, you see the green dots. There are no sort of nice square arrangement. They were just wherever we could put them. They are 20 feet apart, 375 feet deep, and 35 boreholes were needed. It was kind of one of those that actually turned out a very successful project of just getting rid of a cooling tower and boiler and leaving all the systems inside the same. And it became a very efficient system in the administration building. Next one, Kyle. The campus services building is kind of, I'm going to guess, the southeast corner of the campus. It serves their heating plant, the facilities people sit in this building, and we had to go across the street. The red is the building itself. We went across the street with that orange that you see, and those are the boreholes that were done under a parking lot. They were 20 boreholes that fed this building. They were 300 feet deep. Next one, Kyle. And then when we got into the campus-wide system, we looked at the library, the campus services, and the CATS building. The CATS building is a Center for Achievement and Transition Services. Those are the buildings that you see photographs of them. The campus services building was done before the rest of this project. They were supposed to be all done at one time. The college did not have the funds to do it, so we did the campus services first, and then the library and CATS building came in next.
Yep. So
Next,
they called it
next.
so where we demoed it or put this in, I was just going to go back and show you here. So this is the CATS building 10, and then the library is 11. And then in this area here, there'll be some other photos here, is kind of the quad. So that's the area we're talking about next. This is our most recent project there with the geothermal. So this shows the library here. And so to put in the well field, they've got to do a lot of digging. It's kind of a messy process. Also, they took the opportunity. They're like, if we're going to tear all this up, we're going to go back and, try and make it a little nicer and address some other issues as well, sidewalks and ADA access and stuff as well. So this
And
shows,
actually, before you get off this slide, Kyle, I want to just say a couple of words that the president, Dr. Michael Evans, at that time, he's since retired recently. What he said is, so in the spring of 2023, a bunch of guys came over with really big machinery and they ripped our quad to pieces. They scooped up a lot of trees and they tore up all the sidewalks and they scraped off all the sod. It was a real mess. It was a nice quad that they had. It was a mess. And he says they turned a beautiful quad into a gigantic muddy mess. We called it a quad bog. It was spectacularly ugly, in his words, and it forced everyone, faculty, staff, students, visitors, to come and go through back doors of buildings. The front doors which was a quad, and they had to use the back doors. They drilled 80 450-foot deep wells into the ground, tied them all together, and then put everything back, the sidewalks, the trees, the sod. You
yeah.
can keep going, Kyle.
Yep, and I will make one thing. So he did say we tore up a lot of trees. They did remove a few trees, but as you can
Very
see,
few. Yeah,
there
very few.
was trees, and our design took into account to leave the trees. So
Yeah.
we saw how big the trees were, where the roughly the drip line and stuff was, and so it was designed around to save some trees. A few trees they were happy to see go,
Yeah, there
but
was a couple that were dying, and yes, I don't think we let too many go. And so there is a question, Kyle, that says, how long does the installation process take for one of these campus buildings? Um, they typically can go as much as 1 to 2 holes in a day.
yeah,
And then, so depending on how long that takes, this was for multiple buildings that we did. It probably, what did they do, Kyle? They started in the summer and then they started putting things back the following spring.
yeah.
So the quad itself probably took what, about 8, 10 months?
Yeah, well, there's a process. Yeah, it kind of depends. If you have a nice
Yeah,
flat field, you can
yeah,
go do
this,
it, or if you have to spend a little time prepping it. But yeah, roughly one, maybe 2 holes a day is
yeah.
about average for the drilling. And then you have another, depending on how big it is, couple weeks or more to a month to run they have to trench in and run all that horizontal piping or lateraling. So then you got an extra month there. And then you have the work inside the building of installing the heat pumps, but those can both go on
Mhm.
simultaneously. So, I mean, a medium-sized project could easily be 2 to 4 months or something like that.
Yeah, and depending on what else you do, the TJ Majors, just as an example, the first building we did, it took pretty much a whole year, didn't it? They started one summer and ended the following summer. So that's typically the timeline you would estimate for a building that size.
Hmm. But that wasn't just the geothermal part. That was
Yes, it was more. Yeah,
everything.
they remodeled the building. Inside was done up well, and we put in a new mechanical room and stuff. Yep, exactly.
Yeah. And so here you can see the new quad. If you were to go to Peru State College today, this is what you'd see. So most all of these, well, I guess you can kind of see clearly where the old sidewalk was and the new sidewalks. Um, and they got it all, the grass in. You can see there is still a fair amount of trees. And they got a nice new area here where they can sit and gather and have little activities and stuff as well.
And they actually had the state of Nebraska fund part of this remodel, just a part, because now a lot of the stairs, Peru, if any one of you have been to Peru, it's very sloped. Peru, the squad now they had a lot of stairs, which was not good, not accessible at all for handicapped students. And so for ADA ramps, everything changed. There's ways you can get from one end of the campus, from one building to the other, just using ramps, and it's become a very nice, beautiful quad, is what they call it now, the new quad design.
Yep. And so this is kind of a bird's eye view of roughly where the wells landed. So you can see it was kind of right in the middle of things there.
Yep.
And here's the two buildings. And so this all goes into it's all one big well field. And then these are essentially served as one building. So it's two buildings, but the pumps and everything are in one building here in the library. And then the water's just pumped over for its use over here and back. So it operates as one system. Here's another photograph. You can see here's the drilling rig. And so when we were showing you about the first example there with the red holes around the outside, So this truck has to sit almost level, very close to it. You can have a little bit of an incline here that I think up to a few percent. But so this arm thing will stand up straight, and then they will feed the bit down, and when it gets down, then they'll hook on another uh, pipe or attachment, and they'll just keep forcing that bit down, and they'll go through the mud, the dirt, the water, the rock, everything, and then they use water to help pull up the shavings, and that's what you'll see, and then it just kind of makes a muddy mess. So this is one when they're done, they'll cap the pipes after they put it in. They'll let all the grout settle for a few days, and then they come in and they put more. And then they'll come in after this and they'll dig it up down there to connect them all together. Here's kind of a close-up view of that with the grout settling out. And then they'll come in, like I said, and top it off. Just some more views.
Sidewalks getting back in.
Yep. And then here's just kind of a real quick schematic of how it works. So we'll call the solid line the supply. So whether that's cooled water or heated water will come in, the pumps will pump it. You can have an auxiliary heat exchanger, and they have a few of those down there to heat the water just in case. So then that water comes up and it pumps and it goes to the heat pumps. The heat pumps would then use it to heat or cool, and then that return water, which shown in the dash, goes back. A lot of times we design in a bypass so that if the water, so if our ground is roughly 55 degrees and our water is around 50 to 60 degrees, you're not going to get a whole lot of temperature gain by sending it out here. So we'll open up a bypass, and then that saves some pump energy. And so it'll just bypass right here. Generally, the pumps are on variable speed drives, so it'll be able to change the speed and save energy as they slow down. And then here is an example of a building we did in Lincoln. This is St. Thomas Aquinas. It's down on campus, right by downtown. And as you can see in this kind of cool image here, this is the one where we had 620 feet deep wells, spaced 20 feet apart. The outline of the building is here. It's really close to the property line. And then they have a Catholic fraternity right here. And so we've got the wells outside the building and inside, and they had to be coordinated with footings and sanitary and storm sewer pipes as well. So it was a really complicated project, but really successful. It's going on today, and they're using it, and it's working great.
You know, going down 625 feet, it's really difficult to make sure you don't hit other pipes, and it just takes a lot from the installers as well. We sat down with them and tried to get as vertical as possible. And like
Yeah.
Kyle said, it's a
If
very
you're off
complicated,
even just a half a degree,
yeah, you'll hit each other. Kyle said it's a complicated project. It's probably, certainly in the United States and North America, but probably around the world, it's probably one of the most complicated projects I would venture to say. And just getting a little bit into economics, when we start the project, we need to make sure that the geothermal system really does pay back. So we look at different types of systems. And over here, if you look at the top left graph, it talks about the install cost for one of the projects we did at Peru State College. It looks at the install cost of the systems, then looks to the top right graph, shows the first year utility cost. The bottom left graph shows the first year maintenance cost. And the reason I say first year is we put in inflation, the factors that go through. We do a life cycle cost for whether the owner wants it for 30 years, 50 years, 70 years. It takes the cost of replacement into account. It takes the cost of maintenance into account, actual utility costs from the utility company, from mainly the electric company, because we are not using boilers, it's all electric. And then we compare the different systems. So each of the charts that you see out there, they compare 4 different systems. We can compare 8, 10 systems, whatever the owner would like us to do. The install cost, the geothermal was the most expensive, but over the life of the system, and this was a 50-year life cycle cost, the geothermal system did turn out to be the ideal situation. This analysis took a 3% average inflation over a 50-year period. So
There's a
it,
question that kind of ties into this, Vishal,
yes,
about
yeah,
what
yeah,
is the
that's fine.
lifetime of these systems?
Mhm.
The piping itself is just pipe in the ground. It should last a really long time. It's made of a HDPE plastic material. They use it for underground gas lines and other stuff as well. It's warranted for, excuse me, 50 years.
Mhm.
And the heat pumps inside and pumps are generally, thought to last more in the 20 to 25-year range.
Yeah. So the warranty you get on that HDPE pipe, high density polyethylene pipe that Kyle mentioned, is 50 years. The manufacturers say they haven't used it for much longer than that. They expect it to be quite a bit longer than that, but who knows? Gas companies are now actually using that for pressurized pipe, pressurized gas transportation, and so there's a lot of confidence in that pipe. There's another question out there. How do installers measure and check the angle of the well that they're drilling
I,
so they don't run into each other?
I think as they set it up so the trucks don't just sit on the ground on their tires, they can have these little outriggers go out and they can help level it up. So I
Yeah.
believe they have the levels on the truck there and they can check that and see. And then if you're going deeper, they can actually use, so the pipes that connect to each other that they keep feeding down, there's kind of a standard size and they can have kind of a little bit more beefy size that's less likely to deflect when the head hits a rock or something to just go down through.
And actually, in St. Thomas Aquinas, Kyle, didn't they start with some sort of guides that actually made the drill go down vertically, right at the top? They used that and tried to avoid any inclination, any angles to the pipe as it went down.
I think
Um,
that's
so typically, so typically at 100 feet to 300, 400 feet, we have not seen any issues of pipes running into each other. We definitely thought we would run into each other at the 620 feet, but whether it was great installers who knew what they were doing or it was luck, it actually worked out pretty well.
or both.
Yes, or probably a combination of both. Yeah. So we do an economic analysis, just trying to make sure that the system works well. Um, Next slide, Kyle. In addition to what we said, the initial cost of the system is more expensive. There is many rebates you get. You get rebates from utility companies. You get rebates sometimes from the state. The federal government in 2022 had passed what they call the Inflation Reduction Act, the IRA, which is probably still around, but things are changing quickly. And so we don't know how long that'll be, but they also, tend to fund stuff. There's a tax deduction, even though if you are non-taxable entity, there still is deductions that can be given in certain indirect ways. And then there is tax credits. For the next slide, Kyle, that the tax credits could be, if it's in the right part of the country, if it's an area that they're trying to pick up in the sense that they're trying to develop that area, it's not doing very well. It could be as much as 50% of the cost that is returned to you. Now, even for non-taxable entities, which Peru State College and some of the other government entities are, even though they don't pay taxes, they don't just get a credit, they get a check back from the IRS. I don't know the details of how that works. Accountants and lawyers get into that, but there's many incentives out there that can be tapped into. Economics, there is, Kyle, if you want to take this, the cost difference between a traditional system and geothermal is really the cost of the well field. The rest of it is
Mhm.
called kind of a wash.
Yeah.
Uh,
So, because if you're on the inside and you're comparing to like chiller boilers or furnaces or whatever, there's different costs. But yeah, you'll have the inside stuff, you'll have the duct work and all that, regardless of what type of system. So it is, kind of roughly the cost of the well field. Is that what you're trying to get it to pay back? We've seen paybacks anywhere from 5 to 20 years, and again, that kind of depends on, is it a building where they're not using it very often, or they're using it a lot? So kind of the hours of operation will play into that, and how big the system is as well will pay into that payback.
And
So there is,
the more you use it, if you're using it, 10, 12, 15, 20 hours a day, like some colleges do use their buildings, it'll pay back a lot quicker. If it's just a typical office building, like Kyle said, it could be in the 10 to 15-year range. If it's a church or an office that's not used a lot, just a few times a week, it could be um, longer than that as well.
but we said down here, 30 to 40% is kind of a rough range. So if you took your energy that you use on your HVAC and you lower that by 30 to 40%, that's what you could be saving per year. And then the simple payback is just that, the extra divided by that, whereas the life cycle analysis takes other stuff into account, such as, the cost of money and maintenance and all that as well. We talked a little bit about the incentives. So if you're getting the incentives and you're getting 30% or 40% of that cost on the geothermal system back, you could be close to a point where the installation's even close to a wash, and then you get all the savings. The catch is you still have to fund all that up front. So you have to pay the premium and then get your incentive back, and then you get the savings from there.
So there's a question that just came up. What does maintenance look like since pipes are buried so deep? Well,
Generally,
the,
there isn't any in the pipe itself. So I guess the maintenance would be don't hit it with something else. Don't
yeah,
dig into it. And
yeah.
if you remember, I could go back and show you. But so in where the horizontal pipes are, we usually show for them to bury it with sand, and then they can put caution tape and tracer wire on it. So the plastic is hard to detect. You wouldn't know exactly where it is, but if you put a copper wire on it, then you can use that to locate it. So most of the maintenance is just in with either the pump that's circulating the water or the heat pump that's using it to create the hot and cold air. And like you'd have to replace the filter on your furnace or air conditioner, you have to do the same thing on your heat pump. So that's about the same. But you don't have something sitting outside that you have to wash off, or you get the cotton into your air conditioner outside. You don't have a condenser outside to maintain. Uh, you don't have that outside to, so aesthetically it looks a little nicer because you don't have that, and you don't have the noise as well. So there's some other pluses outside of just the utility savings.
So a lot of times, if you did hit the pipe, you're going to hit the laterals that are just 5 feet deep. And generally, we have not had that issue. There have been times when a well or two have leaked and they have been able to trace them and get them repaired. I will tell you, for example, at St. Thomas Aquinas, we made sure that so you don't have any joints in the pipe that goes down. It's all a one-piece pipe.
Hmm.
And in St. Thomas Aquinas, where you actually had the boreholes under the building, we actually made any connections outside the footprint of the building. You came in, you turned the pipe with no fittings, it just curved around and you went outside. So if there was going to be any issues with the joints, it would be outside and accessible. Now, I will tell you also, the way they do the joints, they guarantee the joints almost stronger than the pipe itself. They call it the fusion method or the hot fusion method, and it really becomes a very, very strong joint. So we've not had a lot of issues at all with the pipes. The biggest issues you see with geothermal systems, we've gone in and corrected a lot of other projects that have been designed by others. The biggest issue is the sizing of the boreholes in the well field. Has it been done correctly? Do you have enough heat exchanger capacity to do that?
Yeah, and if you do have a leak, we've seen on one project where they've been able to go in and they use some sort of a tracer gas, and they can put it into the water, and then they use a mechanical, I'll call it sniffer, and it smells for that gas, and they can kind of narrow down where the leak is, and they can test by squeezing off the pipe and seeing if it's still leaking or not, so they can isolate it. It's a little bit invasive to do it, but you can figure out if there's a leak and where it is. And if it turns out to be in one well, then they can, I guess, kind of abandon it. They can close off the pipes to that and keep everything else going. So
You do have a little bit of safety factor in what we've done. So another question that just came up is, do geothermal systems keep up in extreme heat and cold? Supplementary systems, gas furnace, etc., recommended. So we did a project in Wisconsin for a new campus. that was actually funded by the diocese in Rome. Um, Felician Village was the name of it. And when they first came to us, we thought the same thing, that we'd be able to do it in a cold climate like that. And then we did a lot of research and stuff, and there's a lot of systems that have been put in Canada and in European countries that are colder than our climate, colder than Wisconsin as well. They do keep up well if they're designed correctly. Sometimes if there's a residential facility, you can give some backup supplemental heat. Um, we actually, when we first started using geothermal systems 20 plus years ago, some of the projects did have backup boilers. We never used them. And so as we gained confidence in the designs that we do, that went away. So most of our newer systems, we don't even use glycol. We don't even expect the water to freeze. Sometimes we use it if the calculations tell us that we really need it, but otherwise we don't use glycol either, and we don't use supplemental heat. But for safety factor, for insurance purposes, if you really wanted to put something in, then yes, we have done some sort of supplemental heat, electric resistance heat, gas-fired duct heaters. We haven't done that too much at all, but that can be installed as well.
Mm-hmm.
And that was basically a presentation. If you have any other questions, we'd love to answer them for you. It's just a very high level, giving you some examples, giving you some theory behind what it works. Hope it was helpful to you. But if you have any questions, do let us know, and we'd love to answer them.
Yeah, it was a very interesting presentation. Thank you.
Yeah.
And I also just wanted to let everybody know I launched the feedback survey. So if you could take a couple seconds to fill that out, we'd appreciate that. And yeah, just type any questions that you have in the chat too. I actually did have a question for you.
Sure.
Okay.
Uh-oh. Does she freeze? I don't
Well, maybe it was a tough question, and so she disappeared.
On.
Oh,
No,
there you are.
there you are. You're
I think
back.
you were frozen for a sec.
Oh, I was?
Yeah, I
Yes.
didn't hear the question.
Oh, shoot. Okay. Um, I was asking, so you mentioned the open systems that they
Hmm.
aren't
Mhm,
very common,
mhm,
but they sometimes feed into rivers. So I was just wondering if there's any kind of impact on the environment from those
mhm.
systems.
Yeah, I mean, so it'll warm up the water about 10 degrees and you're moving the water from the aquifer to there. So you have to, I think it's what, DHHS, you have to work through with it. So it's not like you can just go out and do it willy-nilly. You have to get the right permits and approval from the state agencies to do it.
They used to do that quite a bit, and then yeah, DHHS as well as DEQ, the Department of Environmental
Yeah.
Quality, gets involved as well. They do frown on that. They want you to actually pull it out of a well and push it back into 2 or 3 different wells. It's tougher. It's easy to pump water out of the aquifer. It's really tough to pressurize it and push it back in. So you generally need 2 or 3 wells for every well you have to take water out. They used to just dump it outside, and the state does frown on that. State, federal, whatever, all the states do. And so we see less and less of that system. It's more like putting in the slinkies in like lakes and stuff like that. But they encourage, if you are using open loop systems, you take it out and try and push it back into the same ground you pull it out from.
Yeah, and I've seen if you do a pond loop, a lot of times you'll see a fountain, and it's not
Mhm.
just for looks, but it acts
Yeah,
like a cooling tower. So
yeah.
it's spraying the hot water up and it cools down as it comes down, and that's how they're dissipating some of that heat to keep the water cool.
That's interesting. Thank you.
Hmm.
Yeah, sure.
And then let me see. Well, it looks like we don't have any other questions coming in, but I
Okay.
appreciate you both taking time out of your night. Super
Oh,
informative presentation. So
someone just
yeah.
asked one here.
Oh,
Does it
okay.
also heat water for residents' homes? Yeah, if you get the right equipment to do it, it can. There's something called a desuperheater you could put on your heat pump, and then that can be used to make your domestic hot water. You can also use a water to water heat pump which uses the geothermal water, which we've been talking about, but instead of using that to heat air, it just uses that to heat water. So that hot water could be used for domestic or snow melt or other things. So
Mhm.
yeah, it's possible with the right equipment.
Good question. Yep.
Like maybe
Any
we
other
covered it.
questions?
All
Yep.
right.
Great.
Just pausing for good measure. But I
Yep. Yep.
think we're good on the questions. Is it okay if I send your email addresses out in the follow-up email?
Sure.
Sure.
Okay,
I'll
awesome.
I'll send you a little link that you can also distribute, and it shows Dr. Evans had sent that. It shows just a little bit of the quad when they pull the sod off and then re-put the sod in. It's just a 3 or 4 minute video. I'll give you a link to that as well that you
Okay,
can send
awesome.
out.
Thanks so much.
Okay,
Well,
absolutely.
have a good rest of your night. Thank you so much.
Yes. Thank you
Yeah.
all.
Thank you, everybody.
Yep. Bye-bye.
Bye.